Hey, everybody. Welcome to Ms.Interpretations. My name is Marin, and this is my virtual campfire. And today, yay, we have the weasels, Dr.
Whoa.
Tapiocaweasel or Vandy, or I hope I spelled your name right.
Yeah.
Okay, good. Because some people do the DER instead of the DE, right?
Yeah. Correct. I think you even well now I can't see it in the description, but I'm pretty sure you even gotten the number of A's and F's correctly.
Well, I have
So
I have friends from
yeah.
the Netherlands and Sweden, and so I wanted to make sure it was
Yeah, you got everything completely right. You got all the capitalization in right, everything. The
right.
people from the Netherlands often get that wrong because in the Netherlands the V wouldn't be capitalized, but
Right.
it's an Americanized name. So
Gotcha,
yeah.
gotcha. But it is Dutch, your name?
It is Dutch. It's extremely Dutch. Yeah.
Cool.
Um yeah, it's I did an internship in the Netherlands actually in 2012 during my undergrad, and it was people people had great fun telling me exactly how to pronounce my name and stuff like that. It was
That's really fun. So how do they pronounce your name? I'm not gonna say how
well,
you're supposed to.
I'm gonna do it wrong. Van der Graaf,
Oh,
something like
okay.
that.
Okay. All right.
Yeah. So
All right. I didn't even look at like a different version of it. Oh, that's too much.
I
Yeah.
like how it looks like I'm a little weasel here if I
You
put my
you
head
actually
to
have your ears, don't you?
it.
Yeah, that's pretty.
Yeah.
All right, we won't let people look up my nose or something like that. Okay, so I have had all right. So I there's a bunch of questions that I would like to ask you about. And it is hard for me to talk about quantum physics and free will without like having also talking about the woo, right? Because there's
Mm,
all like the frequencies and and we talked earlier about Angela Collier, one of my favorite YouTube physicists, up there with you, and she has this thing, and I was trying to find the original because I was like binging her content about a year ago, and
mhm.
I can't remember which video was the first one where she was saying quantum, 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 like people just say quantum and they think it's like, right, amazing. And uh,
Yeah.
those
She's been saying
people
that for a while.
don't
Um,
really.
I
Yeah.
don't know which one that would have been the one that you're thinking of. I don't know if she's done one about she's done one about Michio Kaku, I think. She's done one
Mhm.
about there was a term she invented that I really liked.
Oh, right. It's the let me look because yes, it was she did two videos.
Gelman. I
Yes.
think it was about Gelman or something like that.
Yeah, yeah. So maybe I should just show let me go ahead and show her now because uh if you don't know who this is, she really can make physics interesting for the layperson. And also, uh, she also lets you know when she's getting ready to do a bunch of math, and you can skip it. And she'll put the she'll put the this is what you can go to when you're okay. Let's see. I need to come back and share this. I got too many windows and only one screen. This is very annoying. Uh, where do I go? Oh, I have to add it to the stage. Okay, let's do that. All right, but I'm gonna go back here so I can manage this a little bit better. Um, it's one of her older ones. So if we go here, Crackpots is really
Ah,
good.
yeah.
That's definitely a really good one. And it kind of leans into the Gelman. Okay, so yeah, Gelman amnesia, and then she did another one that was like Mongel, or right? She turned it around.
I don't know if I remember that one. I
I think
haven't
there was
seen all of her videos.
okay. Yeah. So this is Angela Collier and she's awesome. It's just yeah. Um let me go back here.
He is
Yeah,
an astrophysicist.
the Gelman thing was like, wasn't it when? Oh, now see, I didn't rewatch that one.
Yeah,
It's like you think
I
you know
also don't.
something. Yeah,
I don't remember what it was,
it's a
either.
type
It
of
was I it
Dunning-Kruger for
y
scientists, kind of.
yeah, it was something like that. I think it had something to do with about, string theory and feeling, like, lied to by string theorists or something like that, but,
Mhm.
uh, I one of the reasons I think that is because, like, I could tell by the thumbnail that that was also the video in which he went off on Michio Kaku, who is a well-known,
Yeah, yeah,
physicist who has is well known as for his popular science work.
right,
So, I don't know
right.
much about him.
Right,
I've
I
never
gotta
read
go
any
back
of
and
his
watch
stuff.
it again because
Yeah.
I've rewatched a couple things, and every now and then I watch the one that, like, dark matter is not a theory. So,
Yeah, I
yeah,
that's one of her takes that I'm most nitpicky about. Like,
yeah,
her all of her statements about the state of the science are true, and I agree with her that dark matter is like, well, she also doesn't think it's stuff. She thinks it's like, or maybe she does think it's stuff and not an observation. Some people get very persnickety about exactly the right term, and I'm like,
yeah.
it's real, whatever it is. Like, there's something there, and if it's
Right, right. I mean, she's just saying that it's the data, right? It's the there's
yeah,
something there, we just don't know.
yeah,
And there are theories about dark matter, but she's like, but, like, dark matter is the
yeah. Dark
phenomenon
matter
that
is
we're
like
observed.
is the data, and like
Mhm.
not the thing that the data that the like models are supposed to be
Mm.
representing. And I'm kind of like, I mean, yeah, okay, but is like carbon 12, is that just the data, or is it also like actually like, the specific configuration of stuff? Like
Of carbon, yeah, yeah,
it
yeah. Well, that's why I have to watch it a couple of that one,
yeah.
but I did go into the details on that one, like, she has even a place in that one you can kinda skip in order to kinda get back to the theory about it, but her attitude is, yeah, really fun, so, yeah, we've got some magnet, uh, uh, stuff in the chat. I don't know if you can see the chat. Can you see the chat?
I don't why do you have to bring that up?
I did I
What?
magnets do no work is what Al Trucker says, and I think you would agree, maybe. And
Yeah, yeah.
anti-magnetology is fun. These are supporters,
Uh,
these are.
it- y- Trust me, I know Al. He's feigning support. He's lying to you. He's getting ready to
I
when he's
just
throwing
knew.
maggots down.
I don't even go here. Yeah,
Yeah.
okay, so I don't even. Oh, man, this is great. So, okay, so, let's watch, a video, first and see if we can, find out anything about quantum physics and maybe free will. This, first video here.
Newtonian determinism says
Okay. I was just gonna do what's the title of it? I'm
Yeah.
not a
See, this is
professional. I don't get paid for this, so y'all are with me on the ride ride for this.
the oh, hold on. I can
Oh,
tell
yeah.
you the title. Michio Kaku, Why Physics Ends the Free Will Debate by The Big Think. The Big Think, by the way, um, is where my favorite science communicator, um, like author, uh, works. That's Ethan Siegel, who's also an astrophysicist. There's a lot of astrophysicists. You guys don't have to pretend I'm one. Um, and yeah, so he basically everything that he's ever written, I think is great. And he used to work for Forbes, and now he works for
Okay,
the Big
Ethan,
Think.
what's
He may
his
have
last
founded it.
name? What's his
Ethan
last name?
Siegel,
Okay.
SIE or EI.
Okay, okay.
I'm bad at
IE probably, Siegel,
yeah,
yeah.
whichever way.
The German spelling. Okay, okay, cool. Yeah,
Yeah,
alrighty, so I'll check him out. I thought you were gonna say Neil deGrasse Tyson.
I don't. I mean, Neil deGrasse Tyson could be a lot worse. And anybody with that level of sort of mass appeal is going to be somebody that um somebody like me is gonna like have nitpicks with, because that's kind of in the nature of the business.
Yeah. I mean, it is difficult sometimes to communicate science and simplify it to the point where you're totally abstracting out of the actual what
Yeah.
something actually is, right? So
Yeah.
then there's some of his I'm like I'm so far removed from, well, not so far, but anyway, I mean, bachelor's degree in physics, right? And then I taught science in high school for decade, more than a decade, but still, there's still some of his takes. I'm like, really? That's not really how I would explain it. I guess maybe because I try to teach it.
Exactly.
Yeah, yeah.
Yeah, exactly. If we all start sniping each other about that, then eventually the flat earthers are going to be like, see, they can't even
I
agree. And it's
can't
like,
exactly.
like, we understand what we're disagreeing about, at least.
Right.
Mostly.
Totally fine. And he is a very good communicator, and I kudos to him. So there's that. So all right. I don't know how many times I'm gonna have to pause this. I don't know if we just like watch the whole thing through or anyway, here we go.
Whichever you want.
You start talking or you yell at me when you want if you want me to pause it. But I watched it a number of times and I'm not exactly sure what it says. So maybe you can help me out with that.
Okay.
Newtonian determinism says that the universe is a clock, a gigantic clock that's wound up at the beginning of time, and it's been ticking ever since according to Newton's laws of motion. So what you're going to eat 10 years from now on January 1st has already been fixed. It's already known using Newton's laws of motion.
Okay.
Yes. So I wouldn't have started with the clock analogy, but like, it's fine. His point is about determinism.
Right.
And the second half of his point, made the point, I think, better. And I think that's basically right. Newtonian mechanics and basically models of physics before 1900 were deterministic. If you had enough data, then you could predict the future state of the universe in principle.
I've always agreed about motion, right? Inanimate objects, right? But then I've always found it a little difficult in dealing with agents, right? I mean, that's
Yeah.
as far as true determinism, like what the example that, like 10 years from now, what you're going to eat for breakfast. I'm like, really though? Really?
The
I have
idea,
maybe my brain just can't go around that or something.
yeah, because I mean, there's such a vast gulf of difference between the sort of idealized idea that you could predict and the amount of information that you would actually like have to have in principle. Um, Things are too complicated and chaotic. It's
I
chaotic
mean,
in the precise mathematical way that any sort of deviation in initial conditions is going to cause a divergence in final conditions after some amount of time, and it's going to be less than 10 years for something like that.
right.
But in principle, it's according to the physics, it's still true. It's just that you're trying to apply physics to a thing where you don't really have the data for it.
Yeah. It does make me wonder though, the origin of Calvinism and like serious religious determinism, right? Coming about in about the same time as Newtonian physics. Yeah.
Yeah, I tend to think probably, and I don't know anything about really the history of Calvinism, um, but I doubt that they were particularly motivated by the same sorts of ideas.
Hmm.
May One, because one's more about like God chooses everything, and one's more about like, or I mean, you could sort of line them up in that like if God sets stuff up at set the initial conditions, and then it's a deterministic physics,
Gotcha.
then I guess you get both.
Yeah. 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 It's it's a different origin point or whatever, or a different reason why things are determined. That makes sense. Yeah. Yeah. All righty. Oh, let's go on.
Einstein believed in that. Einstein was a determinist. Does that mean that a murderer, a horrible mass murderer, isn't really guilty of his works because it was already preordained billions of years ago? And Einstein said, well, yeah, in some sense that's true. Even mass murderers were predetermined. But he said they should still be placed in jail. Heisenberg then comes along.
I would agree with that, by the way.
Yeah.
Yeah. Like, I mean, are they guilty? It depends on what your definition of guilty is. Like, they still did the thing, right?
Mhm.
Are they morally responsible? Were they able to do otherwise? I don't really care. You can't be having murderers like around.
Right.
Again, you're
Right.
trying to apply, something where it's like it doesn't really matter at the end of the day.
Right.
That unless you can do something about it, like the dude who went up under the bell tower, and decided to just go out with a bang, like
Literally.
turns out, and he wrote down, he was like, you guys got to check my brain. And he had a big old tumor pressed right up against a sensitive area where it has been like demonstrated that people with this type of tumor have dramatic personality shifts. And it's like, in that example, we were able to point at a big contributing neurological factor.
Mm-hmm.
If you look at any system closely enough, then yeah, but it doesn't matter. You still can't be letting murderers just do whatever they want, right?
Right. Right. Right.
And
I don't know why I still have difficult, and I mean, maybe it's just me, but I don't know why I still have difficulty with not having some choice. I know we don't have all choice, right? I know, but yeah.
I
Um
agree. It's disconcerting.
It is. It is. And but then I also get very upset with people for being upset with people who have grow up in a particular world, and in a way their life is kind of determined by their environment, they like I had students that basically were homeless, they just were couch surfing, and it was very difficult for me to figure out, what is it even possible for these students to do homework, because they don't really have a quiet place to actually do anything, right? Or like the last thing they're thinking about is chemistry equations, right? So anyway,
Yeah.
yeah, it's tough.
Yeah, it's very tough. On the whole, I will say, like, I generally agree kind of with his take in this.
Okay.
So
All right. Well, we understand him so far.
Proposes the Heisenberg uncertainty principle and says nonsense. There's uncertainty. You don't know where the electron is. It could be here, here, or many places simultaneously. This, of course, Einstein hated because he said God doesn't play dice with the universe.
Okay, two things. This is when I want to ask you about superposition, right? Can the electron actually be in more than one place, or is this what Heisenberg said? Because this doesn't. I'm
well,
thinking.
so
My
what
understanding. Okay.
Heisenberg, so the Heisenberg uncertainty principle has a number of different facets. Sometimes people think of it as being a statement about like a measurement influences like the outcome. That's not
Not
That's not
exactly.
what I think of when I think of Heisenberg. I think of Heisenberg as being a fundamental inability to specify the expected outcome of two complementary sets of measurements. Heisenberg is about
Right.
complementarity variables. You can't know or even define a position wave function and a momentum wave function simultaneously that gives you an expectation value for both of them, where the uncertainty in the product is less than a certain amount.
Right.
So
Right.
it's a mathematical statement. it does not mean that anything at all can happen for no reason all the time, constantly, forever, which is what a lot of people think that it says. But it does have a connection to whether or not determinism is valid, because one consequence of Heisenberg is that if you know the position to a certain amount of precision, then that limits how well, in principle, you know the momentum, and that means that there are a range, sort of like a momenta that are, consistent, and that if you did a measurement of the momentum, uh, it would be somewhere along that range. Superposition is in there already. Like whenever we're talking about the potential for a measurement to yield different outcomes that are mutually exclusive, when you actually measure an electron, if you say
Mhm.
you have a detector, and when the electron hits the detector, it goes bing, and,
Right.
you have two detectors, and you have a process that that sends one electron, and it goes into one or both or whatever paths, you're gonna get one click. You're not gonna get two clicks. You're not gonna get two half clicks. That's not a thing. That's not how they work. You're gonna get one click, and they are not both going to click. You're not going to observe them both clicking at once. There's a whole thing about branching wave functions, which becomes more complicated, but you're in one branch.
Right.
If you subscribe to that, then you're in one branch. If you subscribe to something else, so but you don't. Quantum mechanics does not predict that anybody will observe two clicks. It's one click, so they're mutually exclusive. And so when you have a situation where the outcomes are described by sort of mutually exclusive kind of probabilities, and you can define probabilities over those outcomes, that's sort of like the heart of superposition. A pithy way of saying it is sort of that it is a situation where it is in two places at once. I have no problem personally using that language. Some
Okay.
people do. Um, the, People get very nitpicky about this stuff.
Yeah, see, I guess that's the hard part for me, is describing as two places at once, rather
Mhm.
than we we can't necessarily, we can't say, we just have these possibilities of
Yeah.
it, and then it's not until we can measure it. Okay, so let me go back just one step to Heisenberg and the way I remember learning this, because I made a C in modern physics. I'll just admit that right now. But the way I remember learning about it is like you can know how fast it might be moving, or you can know where it is, but you can't know both. Is that at the
Yes.
same, like you can't measure,
Simultaneous,
there's
precise.
two
You can't measure them
variables.
both precisely. You
Correct.
can know them both vaguely.
Yes.
There is but there's a limit to how well you can know them precisely. If you know that its position is within this area, then you know that its velocity has to be within some range, but
Hmm, hmm.
you don't know where within that range. And then if you immediately performed a measurement, if you measure the position and you find it here, and then you perform a measurement of the momentum, um, and you discover it's going in this direction with a certain velocity, then even though you just measured the position, you already don't know the position as well as you did before. And that is where people get this idea about it sort of changing what it is. but it's still a statement. It's not a statement sort of about your interaction with it, as much as it is a statement about like what the definition of the wave function. The math doesn't let you define it simultaneously. It is because they're non-commuting variables in
Right,
the
okay.
lingo.
All right, so everybody, there'll be a test on this tomorrow. Is this why? Well, maybe we can finish. Let's finish this. I'll ask you that in a little bit. Let's finish this little video, and we'll maybe yay! Hey, Mark. Okay.
Well,
Let's.
hey, get used to it. Einstein was wrong. God does play dice. Every time we look at an electron, it moves. There's uncertainty with regards to the position of the electron. So what does that mean for free will? It means in some sense we do have some kind of free will. No one can determine your future events given your past history. There's always the wild card. There's always the possibility of uncertainty in whatever we do. So when I look at myself in a mirror, I say to myself, what I'm looking at is not really me. It looks like me, but it's not really me at all. It's not me today, now. It's me a billionth of a second ago, because it takes a billionth of a second for light to go from me to the mirror and back.
Okay. That last bit, like, okay, okay, it's true. You never step in the same river twice, sort of deal.
Right.
But I kind of thought it went a little bit off the deep end with like a little bit of deepities at the end there, I think. I mean, it definitely is like you in some sense, but fine. He made it sound like the idea that there is free will or that there is randomness implies like, oh yeah, no, there could be free will. Like how?
Yeah, that it's too short to actually. I mean, maybe he has a good point. Maybe he's got a good idea. He just didn't say it.
Yeah.
There, right? Because I think that's one of the parts about this discussion that is a little hard to wrap my brain around, is that there's a difference between uncertainty and randomness.
Yeah, those things are different for one.
Yeah.
And there's a difference between but if it's impossible for you to predict, like, you know, what you're going to do next, it's not deterministic.
Yeah.
But it's also if you don't control it, if it's random, then it's not will. Right? Like it's not
Right.
it doesn't fail to be free will because it's not free. It fails to be free. I mean, sort of because it's not free, but more because it's not will, really. By the way, I'm not a philosopher. I'm just kind of using
Me
words.
neither. Me neither. Let's solve one of the hardest problems in philosophy. Let's do it now.
Yeah. But because but like I've heard this question sort of posed as a dilemma of sorts, which is, okay, either the choices that you make are determined beforehand or are determined by something, or they aren't. If they are determined, then you don't have free will, right? Because the thing that determines them is what determines it.
Yeah.
And oh no, did I?
You froze, but I
if
don't
they
know
are determined, then you also don't have free will because you can't choose. So now I used to find that not particularly like convincing.
Can you say it
based
again?
just off
Because I got
vibes.
distracted because you got frozen. Wait, if you'll say it again.
If your decisions, so your brain makes a decision. Either it makes that decision for a reason, like there is a process that determines that decision, in which case you don't have free will because your will is a consequence, a deduction of that process, or there is no reason, in which case you still don't have free will because you didn't. I mean, you didn't do it,
Right. Right.
and it's. I think that proponents of free will, which might say, okay, yeah, but you're sort of equivocating what you mean by determined between those two, and you're sort of like for the first example, it's like, okay, yeah, no, I agree they're not determined in that way, but then in your second example, they think there's sort of a middle ground there,
Right.
and the idea that quantum um, uncertainty could be a space where that kind of wiggles in, it's not obvious to me that can't be made to work. You might be able to make that idea work, maybe, but it seems I don't see it. You'd have to convince me. You'd have to
Okay.
convince me that the idea that there is this sliver of ambiguity means that ambiguity, which looks like randomness, is actually will.
Right. Yeah. There's the space for it, but not a mechanism to show that it actually happens. Okay. So let me summarize what I'm thinking that you're saying. And in the Newtonian idea that of, if you have enough information, then, and you have all of, uh, you can, there's a determined place and time and things that, are that the world is going to be a particular way, right? And that can happen with people too, with the brain and all that. So that's like that hard determinism kind of perspective. But when you think about quantum systems, which, chemical reactions and things like that happening in our brain are quantum systems. And so there is like, you have to think of the quantum system as uh, there there is randomness in that, right? How something might happen, where electrons might actually be, and how they might actually move in a system or at one, right? We usually follow one. There is randomness in it will be here, it will be there. Okay. But and that is an initial way of saying, yeah, because of superposition, there's a choice. There's, something that can, the electron makes a choice about where it's going to be or what spin it's going to be. Um, and that might be the free will thing. But randomness is not choice, right? It's not free will. We don't know why that electron decides to be here instead of there, decides, or has a spin up or spin down or whatever. But we do know that its pair is going to be the other way. That's
Yeah,
that's what we right. All
yeah.
right. So I just added that little extra bit. But is that
It,
a little bit of what
yeah,
you're saying?
yeah, exactly. You would have to demonstrate. You'd have to demonstrate that there is some mechanism by which, I don't know, like consciousness or whatever,
Hmm.
is stepping in and doing something that, uh, like, is will like, is
Yeah.
choice like,
Right.
and I like it feels like there could be like maybe a middle ground there, and I used to sort of be a lot more compelled by that.
Hmm.
Um, uh, but nowadays I sort of, as I've become less disturbed by the idea that there isn't free will, I've become
Accepting.
more accepting. But like my actual like opinions on the sort of specific like facts on the ground, as it were,
Hmm.
hasn't particularly changed. um,
Right.
but it's like maybe because it does feel like there's an equivocation. It's like, okay, when you say it's determined or it's not determined, well, what is if it's determined, but like by me? And then they'll come back and like, oh yeah, but you're begging the question. It's like, yeah, this is the problem. It's like it kind of
Yeah.
feels like both arguments. There's
Right.
something missing in how we're trying to describe it. It's which is very common, I think, in the intersection of physics and philosophy, because
Yeah.
they talk about, most of the time they talk about the world in kind of very different ways
Hmm.
up until they sort of don't, and then you're dealing with like formal logic, and it's
Yeah. Yeah.
very precise, and I'm not equipped to deal with it.
Yeah. I do have to interrupt for a quick second. And I don't know, Titan. Titan is asking, I'm just the messenger. Is quantum uncertainty reduced in a strong magnetic field? I'm sorry.
I don't think you are.
No,
I think you're a liar.
how dare you, Titan? I'm gonna have to take away your mod status. I don't know. Come on, man. Yeah.
Well, he also made a comment that I think he's saying that what I'm saying sounds suspiciously like compatibilism. I I don't no, because I think there's a version of it that like could be. Compatibilism says that that means that that is equivalent to free will because it's like just as good. I don't believe that. Like free will to me, when I think of free will, I think of like sort of classical like libertarian free will as I understand it, which is like
Hmm.
the ability to have done otherwise in some meaningful way,
Right. An actual choice.
an actual choice,
Yeah.
and not one that is due to, you know, whether an electron spin resolved as up or down in a neuron somewhere, like
Right.
an actual like choice. And I would say that free will, as I understand it, would require that. Compatibilism says that like even if you don't have that, you still have free will, and I'm like, nah, that that's not free will then. That's
Yeah. Yeah.
yeah.
Yeah. All right.
That's
I'm teasing, Titan.
non-involuntary action.
Yeah. All right. So I think Titan would like to debate you, but yeah, maybe one day. I'm teasing with you. Okay. So I think is this there's two things that I'm thinking, and I'm going to come back to some more comments because some people had some cool things to say, but I don't want to forget to ask you about this kind of stuff. And that is, I mean, as we're walking around in the world, we think we have choices, right? And for me, like I think that so we might as well like there's one way, well, we might as well just can talk about it like we have free will because we think we have choices and we act
Yeah,
like we do,
absolutely.
even though we're determined, like we still,
Yeah.
it's like I can't really think about the fact that I'm not making the choices. So there's that, but it's the moving from the subatomic to me walking around in the world, right? I mean, that's like a huge leap, right? And
Yeah.
so I have talked with my friend Tobias over in Hanover about hidden variables, right? It's the same, a similar problem in Newtonian physics as it is in quantum. That like there's like who can compute the all the variables to actually figure out mm,
Well,
all of this stuff, right? I mean, like my whole semester of thermal statistics was studying a particle in a box, like it seemed like
yeah.
that's like one particle in a box, like the behavior of that particle in a box. So that, do you see what I'm saying? Like how,
Yeah. Well, the hidden variables is a sort of a term of art that
okay.
has a pretty specific meaning generally in regards to sort of entanglement and regards to um, this idea of like local realism. So an idea that I felt like you sort of skirted near earlier was when I was talking about the electron, and you have some apparatus that deflects it either this way, and it hits one of these two detectors. Um, and the idea that like before it like hits the detector, um, it secretly there was hidden somewhere in the electron in the system in hidden somewhere physically in principle there is a quantity that we can't see with the theory of quantum mechanics, but that's because it is in Einstein's language an incomplete theory of potential, but there is something there that determines or that is predictive of what will happen. And if you pair that with localism, which is the idea that like nothing that can happen at one location can, to put it more broadly than it, and a little bit, I think, more precisely than the idea that if you have something here, then it can't affect anything that happens further than the light speed distance away. Like for something here to affect something over here, you have to wait the light travel time between them. And that turns out, if you put those two together, then you can say definitively, and Alan Aspect won the Nobel Prize in 2022 for this, and I met him.
Cool.
Yeah, he was a visiting professor and at Boulder. Actually, I think at the same time when Angela might have been at Boulder. I didn't know her, but
Yeah.
I know who she worked for and everything. But he won the Nobel Prize for his Bell inequality experiments, which basically categorically demonstrate that, as stated rigidly, local realism is falsified. It is not compatible with experiment because it turns out that if you would expect correlations between different measurements to look a particular way, and this is this is fairly robust. It is a thing that you can reduce to sort of a textbook problem, and you can do linear algebra, and you can show, okay, if there is anything that satisfies this criteria, that if we knew about it, it would predict, and stuff that's far apart can't have any sort of faster than light correlations, which, by the way, and this is a very subtle point, does not mean information can travel faster, which is a very weird thing to think. But all of those things are true. Einstein was wrong. I think that he would have had to. I think he would have conceded that if Bell had done his analysis, because Bell did his analysis that predicted, okay, if this is true, then this is the experiment that you could do to detect it. That analysis, I believe, was published after Einstein died, and then the experiment wasn't performed until another decade after that.
Okay. So are you talking about spooky action at a distance?
Yes.
Okay.
Yeah.
Okay. So can you clarify
Yeah.
what that is?
Spooky action at a distance. One way where it doesn't seem spooky at all is the thing about the electrons. If you have a click in one detector, you know that there's not a click in the other. If you knew that there was one electron, that doesn't seem spooky at all. Okay. Imagine instead you had two electrons, and one of them is spin up and one of them is spin down. And you send them, and then you send them in opposite directions, really, really, really far away. And you did it in such a way that, according to quantum mechanics, they are not actually spin down and spin up. They're both
maybe
individually, maybe they're both things, right?
Right.
Is genuinely the way I like to talk about it. I tend to embrace that, in two situations at once language personally. But if you have that, and then you measure one, and you learn and you know that together, though, no matter in whatever configuration, you don't know which one individually they are, but you know that their net spin is 0, so they're always in opposite direction. I always do it this way instead of together. And so then if you measure one, you know that if the other person measures it along the same direction, and that's actually really important in subtle ways that I will not have time to get into.
Okay.
But you have to measure them along the same axis. If you measure them along slightly different axes, then this is actually where you get the predictions that Bell came up with, which is why he was brilliant. But for sure, as far as you can in science, what a measurement along that same axis of the other electron all the way over there, way too far away for you to have any impact, you know what it will be.
Yes.
But so you're like, okay, well, that means that either something is happening faster than light, it seems, or there is actually secret information, and the electron that I looked at already was secretly this way.
Right.
And that the combination of those, one of those it has to be like wrong, because it turns out that like you can't. So the spooky action is that somehow what you've done affects the state of affairs over there. Like now that state of affairs is determined, even though it is outside of your light cone. Like what you do can't affect that. If you guys perform the measurement, a nanosecond apart, but you're 300 miles apart, light can only travel this far in 1 nanosecond. Literally, light travels about this far in 1 nanosecond. So if it can't be, are they both affected? How is it that they both
how do it know? How does it know?
How does it know?
How does it know? How does this electron over here know that one is now spin down and this one is up? Right. I mean right. But I've heard it described as like a pair of socks. Put a pair of socks in a box. Yeah. And pair of shoes. You put a pair of shoes in a box, not a sock. Socks are not going to help. Okay, you put a pair of shoes in a box, right? And somehow you separate the shoes.
Yeah.
And one is going to be left, and then the other one is right. But that doesn't quite fit, because in the box they already are left and right.
Exactly.
But in quantum, they're not already left and right.
Because if they were, and you did that same experiment a bunch of times, but each time you sort of rotated the box, there's not a reason that rotating the box would affect the measurement in this, because shoes are not sufficiently quantum for this to be apparent. Then there are experiments, and the Bell tests are that class of experiments that would give different outcomes.
Yeah. Okay, well,
and they don't. So it's like, how? It's like, why? Like, what is happening? Information isn't traveling, but something about a correlation suddenly becomes like knowable. Like something about the state of affairs of the universe, and including in places that are distant from you that you didn't know before, but no information is traveling faster than light. Those feel contradictory.
Right.
I totally get it, but they're not contradictory. So it's like, so what is happening? The best term we have for it is wave function collapse.
Yeah. Which is hard to explain. It's hard to explain to somebody I told you I had sigmophobia for decades, right? Did I tell you that?
I don't know what that is.
I made it up. Sigmophobia is fear of summation signs.
Okay, I was wondering, because they're hard to write.
Because I had such a terrible time with thermal statistics and thermodynamics.
Oh, that's legitimate.
And every time I was like, I don't know what this means, because I just could not do calculus or differential equations in college. I didn't understand it. My brain was not ready for it. So anyway, I have math dreams about having to go take the ordinary differential equations exam, and it was my nightmares for a long time. So, but yeah, what is the collapse of the wave function?
The collapse of the wave function is basically the statement that, or the idea that there are certain ways that you can interact with a particle or with a wave function that change its that's way too technical.
Yeah.
It's in
I mean, it's a
in layman's
solution.
terms,
Is it not a
it's the thing.
solution?
Well, it's when your observation forces the outcome to be like one
A
of the
solution.
solutions to Schrodinger equation.
Okay.
It's when it goes from being multiple things at once to being one of the things and an observable one of the things.
Yeah.
Um,
So can you use that interchangeably? Like, I mean, you assume like okay, Kip, seriously, I'm gonna have to
no,
kick you out.
don't why'd you have to put it on
I'm
screen?
sorry. I have to kick him out. I know. I know. It's just we already, yeah. Yeah. Why are you like this?
Yeah.
Yeah. So can you use, is that interchangeable with saying that you've made an observation? I mean, because there has to be a solution or
They're
kinda, maybe.
so, yeah, they're pretty close.
Okay.
I wouldn't say they're interchangeable.
Okay.
Um,
Or is a way of
when you make an observation, or a measure there, but I mean, there's this idea of like weak measurements, which I don't even really fully understand, which you like gain some information, but like not enough. You can sort of spread a measurement over like a bunch of them. And I genuinely don't even understand entirely how weak measurement
yeah.
works. Um,
Yeah.
even
Yeah.
like it's very much
Okay.
my field, but
All right. Well, I feel like I don't not know as much about quantum as I did before. I know a little. I I don't know if I know more than I did before, but I kind of feel a little bit better about what I thought I might have known. Yeah, that's what I'm
it,
saying after
it's
talking about this. Yeah. Is this true that
these
go ahead.
some of these like all of this stuff it really is. I think it really is hard. I think people that pretend that it's like obvious and easy are doing one, are fooling themselves. Two, they're geniuses and they're just like way smarter than the rest of us. It really is hard. A lot of the things that you think like you like, wait, that doesn't really make sense. Like you're you're right. It doesn't make sense because our expectations of like what like how things should make sense don't necessarily map to like the way they actually are.
Right. What
You
we
do develop
observe.
an intuition for these things eventually. You can kind of get a sense where you're like, okay, I that I feel like there would be like a weird way of kind of doing, this kind of idea, blah blah blah. Yeah, it's
Yeah.
hard.
Um, should we look at this saving little video, some of it,
Uh,
or
yeah, sure. She like hers wasn't particularly long, right?
it's not very long. It's a few. How long is it? Oh, I can't see here.
Yeah, let's take a look.
All right.
Because
Is
also I know like the
consciousness
Wait,
second
wait,
linked
wait.
to
half of
Hold
it
on.
qual?
Sorry. Sorry.
is like a brilliant ad or something. I
Yeah,
think.
exactly. So it's about 5 minutes, but
So
yeah. So we don't have to do the whole thing. It's just that I'm not really sure. I don't necessarily understand what she's talking about as far as the article. I want to go back to the article, but anyway, so this is quantum physics prevents free will.
yeah, so one thing I will say, this Sabina has, I think, got a little bit off the deep end
A
in the
little,
last
maybe a
in the
little.
last year. That doesn't mean everything she says on physics is like wrong. Um,
Right.
but yeah, no, she
I just think
yeah.
I just think she's in it for the clicks.
Yeah,
I
it
think
really does seem that way.
that sometimes she stokes
I
controversy just because it will bring more views.
Yeah, I have to agree. It's really been sad to see.
Yeah. Yeah.
Yeah.
All righty. So let me come back here. Uh, by the way, I was just trying to see. I have 493 subscribers, by the way. Just letting everybody know if you aren't subscribed, I'm very close to 500. Just saying. Okay, let's watch this.
Quantum physics. Some physicists, like Roger Penrose, think so. And given that we don't know just exactly how the human brain works, it isn't totally crazy to think that maybe quantum physics plays a role in it. But, plot twist, a group of physicists have now argued that actually the human brain can't run on quantum physics. Well, that's new. So let's have a look at the paper.
Can't run on quantum physics.
Like, as stated, that's obviously nonsense, because like your brain runs on like chemistry, and chemistry runs on like quantum physics. But that's I
Yeah.
think that's a straw man of their argument. That's like also not what she's making. So I will have to give a little bit of charitable interpretation, both on her part and on the part of the people she's covering. Because I think if I remember correctly, I think I actually kind of agree with her take, which is
Okay.
that she doesn't agree with their take.
Doesn't agree with their take. Yeah. Okay.
Yeah, she doesn't agree with their take.
Yeah.
That doesn't mean that they're wrong in their conclusion about, free will, but their reasoning was not convincing.
Yeah. Okay. Alrighty. So this is all turning out to be not as woo as I thought. So I'm just gonna say that. It's nowhere close to the kind of woo that you and Maya cover.
Correct. As far as I know. Yeah, but let me listen to it again.
Right. Okay. Should I just keep going?
No. Yeah, go forward. Yeah.
Physicists distinguish two different types of theories: quantum physics and classical physics that works without quantum effects. Classical physics is the world of Newton and Einstein, where objects have definite locations and velocities, and you can predict what they do. In quantum physics, that isn't so. Objects generally don't have all their properties definite. They can be in multiple states at once. They are subject to an inevitable uncertainty. And most importantly, in quantum physics, we can't predict what will happen. We can only predict the probabilities for what could happen.
Okay. So I do have one quick question about this. And I'm sorry. I totally forgot to turn off my Wi-Fi again. So it's probably a little jumpy. The first thing that she said was that something can be in multiple states at once. Like, I don't like that. I don't like that. That sentence. Is that what that's saying? Is that what quantum says?
I would agree with that. Yeah.
It is
I
saying
would.
that. That's what you mean. I mean,
I mean, people don't like it, and I'm like, I don't know what to tell you. It really, I think that is a totally good. I think that but then what you don't like is like the way physics works. But I think that is a fair way of using words in a sentence to describe the way physics works. Some people will fight me on that. And I'm like,
it's just
okay,
a shorthand way of saying superposition.
Yeah,
I mean,
I think that's a shorthand way of saying superposition. Personally,
see, I might be in different places to me, but that's not the same thing. Then, like, something might be in these different places, rather than it is in. In two places.
If it isn't in multiple places, then it is in one place, and we've proven that it's not in one place. That can be proven. That's what Bell did, basically, was prove that it's not in one place. So it has to be in multiple places. So
why do I have trouble with this? Why does this upset me?
Because it sounds like, because it like sounds silly and absurd, and it's very counterintuitive. Like you've never like held something in your hand where that makes any sense.
It don't make no sense.
Okay. When you slow down a particle, or if you send photons through two slits, good old fashioned double slit experiment, but you you send them through one at a time, you still get an interference effect. And you get the interference effect that happens from if it went through both slits, but there's only one photon. You can do this, by the way, with electrons. You don't have to do it with photons. It's interfering with itself in a way that only makes sense if something like the wave function went through and obeyed something like the Schrodinger equation to very excellent accuracy. It went through both slits at once. But if you put a detector at the slits, then you're only going to measure it at one of them. I've done these experiments. When you sort of see the data, it forces you to be like, okay, well,
that's the only way we can explain it, is that it
it's,
has
it's,
interference.
it's like, do you have a better way of explaining? Do you have language that is similarly representative of what is happening, that is remotely as short as two places at once? And I don't really think I think that, like, not really.
Yeah, see, I guess this is my question. Undefined state or multiple states? And I think undefined states, but you're saying multiple.
I'm saying I mean, it depends on sort of what you mean. Like, if you mean if the idea, well, because I think people think that if the state is undefined, if the state is defined, then I think if you mean it's defined as being certain of one outcome, then no, it's multiple states. But if you just mean undefined as like, well, they're sort of the same thing. I guess we'd have to be more precise. It's like you can say with very, very, very high confidence, approaching absolute certainty, that certain things are not going to happen, because the probability amplitude of that outcome is
just not likely.
Is negligible. It's not. I mean, if I wasn't hedging so hard, I would just say it's impossible, right?
Right, but you're a scientist. You can't say that.
Yeah. So, but it's. I mean,
there's multiple
it isn't.
possible
Well, like when
states.
we write it down. We say, okay, at this, like the wave function starts in this. Like if you start in a situation where you do know exactly the state, you know the outcome of any measurement that you would perform on it at that moment. And then you hit that atom and you hit it with radiation of a certain wavelength and a certain intensity for a certain amount of time. After that time, you do not know if it's going to be in the excited state or the ground state.
Mm-hmm.
But you can say with very high confidence, if you had 10 million of them and you measured each one of them, what the statistical distribution would be. You can make,
and it would be one or the other. It would be an excited.
It would be one or the, for each individual one, it would be one or the other. But for the entire ensemble, if you hit it for like half of the amount of time that it takes to flip the state, then half of them would be spin up, and so it's this weird combination of things that you do know and things that you don't know. But when you're writing it down, when you're describing the state after hitting that atom with that laser, you write down and, like, you say, okay, in the basis of energy states, I write it as this state, as this amount in this state, this probability amplitude in this state, and this probability amplitude in this state. There's a bunch of other states also, because atoms have lots of states, and those are all basically zero, and you kind of ignore them.
I don't understand what you just said. I'm sorry.
That's fair. When we say it's in multiple like states at once, we mean that precisely. We mean, like, literally, you can articulate how much, like the probability amplitudes, but that doesn't mean you know what the outcome will be. You just know it's like you can say if you flip a coin, you know what the probability is of heads or tails. If you roll a standard 6-faced die, then you also know the probability of that, but it's a different probability, you know?
Right. Okay.
You point the laser at it. You got a particle, and you got laser. I don't.
You can actually do it. You can actually.
Yeah, yeah, you can actually do that, and like actually you can. I mean, for us, like we have strontium atoms. We have a laser at 689 nanometers. We have about ballpark, I think 200 milliwatts of that comes out and forms a little dot about that big. And under those conditions, it takes about on the order of 500 nanosecond the ground state to the excited state. And then the atom is so the atom has half been excited and half not been excited at the same time. And since part of its amplitude has been excited, that part of the amplitude has absorbed the momentum. So now this atom is moving in two different places at once. And then we shine them with lasers again and we make them go back. Like, this is exactly what we do. We split them apart and put them together, but not in the way that you think of, like, atom bombs splitting them apart. It's a totally different type of splitting.
It's a quantum thing. It's a quantum splitting. Okay. Oh my gosh. So there has been some really cool stuff going on in the chat here. And I see a kinetic talking about this conscious observer theory and theories or whatever.
Oh yeah, that's one of the rougher ones.
Yeah, so I think that's like a whole nother thing to talk about at a so I'm making a note. So I just want you to know that I'm seeing this conversation.
We won't have time to go into that, no. But that's a whole nother like discussion.
Well, I mean,
consciousness has nothing to do with it, in my opinion. Like to me, you can explain these things in a sort of objective theory that doesn't require conscious observers at all. I think that wasn't understood very well in the early days, and it was understood remarkably poorly by some very influential people. So
yeah. So we can talk about that, but then also, then there's this. She was talking about like free will and then consciousness, like in that's what was bothering me about what's Sabine is saying here is, like the title is Physics Prevents Free Will, but then she's talking about quantum states or whatever quantum systems are related to consciousness. And it's like, I don't understand. Why are you mixing these kinds of things? That's part of why it's difficult to suss out.
Well, to me, those two things do seem inextricably linked. Like, how do you have free will without consciousness?
Right, but we can have consciousness without free will.
Yeah, I don't think she disagrees with that.
Okay, I'm just saying, yeah.
She's just pointing out that the way I think she's trying to like lead into it is by saying, okay, consciousness is a thing about like brains and how brains work. Brains are physical objects. Physics has quantum mechanics, therefore these ideas like are connected by those threads, I think is basically the point that she was making.
Yeah. Okay. Alrighty. I'm being harsh, I think. Okay. Let's see what else. Let's see if we can figure out what the actual article is about.
We might be able to say, for example, that a particle has a 50% probability to go right and a 50% probability to go left. But we don't know what the particle did until we go and measure it. Many physicists, including Niels Bohr, the father of the Copenhagen interpretation, thought that this indeterministic element of quantum physics is where free will hides. There is our feeling that we have several different possible actions we could take, of which we then choose one. The idea is that this might be because these possible actions are in a quantum state And it's only our choice that transforms one of these many possibilities into one actuality. However, most physicists today think that there aren't really two separate regimes of physics, one quantum and one classical. Really, everything is quantum. It's just that for large objects that we encounter in daily life, the quantum effects become so small and subtle that we can't see them. It's much like we don't see the effects of Einstein's relativity, not because they're not there, they're just too small. The authors of the new paper now say that this can't be, because humans can really only have free will if quantum effects truly go away. It's not enough that we just don't notice them. To be concrete, they don't argue so much about free will, but rather agency. That's the ability to make decisions internally without being strongly dependent on external input. This is because you could say that your phone makes decisions in some sense, for example, whether to send you a notification or not, but whether it does so or not is determined by your input. So your phone has little agency. For us to have agency, the authors...
Okay, are we following? I don't want to let it go too long
Yeah, I think so for one thing, I don't know if she correctly portrayed the positions of Niels Bohr and whatnot. She may have. Niels Bohr believed a lot of. Apparently, he was a very, very eloquent speaker, but some of his writings are a little bit difficult. I don't know. She didn't explain like the argument. She explained that the people of this paper said that free will can only exist if there's no quantum effects. Like, presumably they have an argument which he didn't give at all.
Right.
So I don't like. I'm not convinced by their argument, which I haven't heard. I haven't read the paper. She didn't. If I were them so far, I would not be particularly impressed with how she represented our argument. She didn't even like summarize the abstract really, because I would like to know what sort of premises they are working from to get to that conclusion, because that's just so not obvious to me.
Yeah, and I'm actually kind of interested in looking at the paper now, because she's talking about this model. Maybe I will let it go a little bit and see if this. I think she connects this idea of a model of the world onto the brain. I think she connects it to the paper, but not very clearly. That's why I kind of end up being kind of confused. So
argue we must be able to simulate in some sense our environment and the results of different possible actions. This means we need to map this environment to our brain multiple times to consider all possibilities. However, there is an obstacle to this in quantum physics, which is the no cloning theorem. This theorem says that you can't make a copy of an arbitrary quantum state unless you destroy the original. It's a mathematical property of quantum physics. There is no way around this. So the authors say if our environment has only quantum properties and the human brain has only quantum properties too, then humans can't make models of their environment. They don't have a world model, as the authors put it.
Yeah, see, this is what I don't get.
Okay, now that I better understand what they're saying, that is, I think, it just an on its face pretty silly argument that the authors are making. Yeah, no shit. Like, so the no cloning theorem is basically if you have an arbitrary, like, fully described quantum state, you cannot in general, like with full generality, it is not possible to just make an exact copy or clone of that in some other location. It's not as deep as it sounds. Actually, this is something that you learn in undergrad, like quantum mechanics. No, I guess in grad school, but you learn about it in school. And there is like a mathematical proof. It is a theorem that arises from the mathematical axioms. I don't know why the hell that would have anything. Why you would then say that you can't make a good enough model of the world? Like models aren't clones, right? Like a model of a
Right.
thing isn't a clone of the thing. Like what?
Right.
That's silly.
Yeah, that right. I
One
know.
might say,
Oh,
okay,
sorry.
but we
Oops. I like this picture, by the way. It's my
Yeah,
favorite.
no, and I think that she's pointing out basically the same thing. Like, yeah, like really, that's not that's not how brains work.
Yeah. Yeah. There's something going on in the chat I don't understand, but maybe okay. So yeah, she's
don't
kind
need a
of
particularly good model of the environment. Like if we try to decide whether to eat pizza or noodles, it's not like we need to have a model of exactly each atom in the pizza in our brain. Still, the authors say if the
Okay, hold
pizza is
on.
really a quantum state,
If she's gonna talk about pizza and noodles, doesn't
right.
she have cookies and a salad?
But I could not get past that. I'm sorry. The editors are not listening to what she's saying. What is going on? Yeah.
and if you want to make multiple, if only approximate models of the state, then the fidelity of your model degrades rapidly. This means
Yeah.
basically that your model is bad. It has little resemblance to the real thing. Then they conclude
Good
that this
enough.
means that a quantum computer can't develop true agency. And more importantly, for us to exist, quantum physics needs to break down somehow.
So are the cyborgs and the computers and the AI that they're not going to take over the world after all?
Oh no, they're definitely gonna take over the world.
I was thinking they would, but
Yeah,
yeah.
no, that's yeah, we're definitely like screwed.
Yeah. Yeah. Okay. Yeah, we have created our own demise. Okay.
It was inevitable.
Yeah.
What are we to make of this? Well, it's to my knowledge a genuinely new argument about quantum physics and consciousness, which is why I think it's interesting. That said, I'm highly dubious about their claim that the no cloning theorem would forbid us from making even approximately correct models of our environment.
Correct.
This is why I give this paper 6 out of 10 on the bullshit meter. I have a feeling that someone's going to prove them wrong in the near future. But even so, it might become a fruitful line of thought. At the very least, I can now use this
Oh,
paper to blame all my bad decisions on quantum physics.
yeah. Okay, that's the end of it. So I can blame all my decisions on quantum physics. I mean, it's not going to care if I blame it.
Yeah, no. I am in the awkward position of having to agree with Sabina's take here.
Is that
Even
strange?
though,
Yeah.
yeah, because I mean, I don't watch a whole lot of her videos anymore because of
Yeah. Well, yeah. It just came up when I was searching on free will and quantum, right? And I'm like, yeah, so I'm gonna see how this kind of pans out. But yeah, I
don't know why people like she's like, I imagine somebody's gonna disprove it like soon. I'm like, yeah, probably somebody will write a paper. Like, why would you it's
why address
why would
that,
you bother?
right?
Yeah, like it's
not really.
just not a very substantive argument. I don't even think that argument is. I think it's more interesting for what it says that somebody actually went through the time and effort to write that paper and publish it.
Yeah.
But that's like stoner logic, honestly. That's what it feels like to me.
Yeah. Yeah. Okay. Well, I didn't get an answer. I still we still have our problem of consciousness and free
It's a
will.
hard problem.
It is a hard problem. Yes, it is. And we don't have any free wills, and that makes me mad. But yeah. But I mean, so it's not okay. So I guess I go back really quickly to so hidden variables are not the same. It's just the many variables, the multiple variables. It's not like we can really know. It's not like we can really know everything about everything because we don't have the computing power and all of the variables that right? So in a way, we still
Yeah,
like
well,
move around in the world like we have free will because
it's also that it turns out, or you don't, the amount that there is to know about quantum systems is less than people suppose sometimes. They suppose that there's this hidden information about which state it's secretly in, and there isn't.
Mhm.
So it's sort of this kind of weird paradox where we know everything. It's just that we expect there to be more to know.
Well,
And
but I'm saying that the hidden variables problem is different than all the multiple variables because we have so many different interactions, like
oh yeah,
the
yeah.
three
One's a
body
problem of
problem, right? We just
well,
have
yeah,
too
yeah,
many.
yeah. Yeah, those are they're different categories of problems. One of
Yeah,
them is a problem about insufficient information, and one of them is sort of a problem about the intrinsic nature of the wave function.
yeah, yeah. All right. Well, just to uh I mean, some of the chat I don't understand too. So I have to see why this is happening here. Okay. Where did it go? It was after this. Yeah. He's not gonna let you go.
I mean, well, no. See, the thing is that I am able to ground every statement that I make in the metaphysical ultimate that has been revealed to me by special revelation of Jesus Christ. Okay?
It's a God thing.
And if you don't have that grounding for your metaphysical substrate, then how are you able to assert the truth or falsity of any statement?
You absolutely must presuppose everything that I presuppose. I mean, seriously. Yeah.
You do.
Yeah. 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 So, but I
Exactly.
mean, so Titan is wrong then. Your non-contingent universal that you build this foundation on obviously is Jesus Christ. Yes.
It's yeah,
Yeah.
direct
Okay.
special revelation of Jesus Christ.
Okay.
Absolutely.
This is good. This is good. So, yeah. All righty. Yeah, there was much going on here. So, kind of all right. And I don't know. Okay. I know that you said this. Did you say this twice? I don't know who that is.
I don't know who that is either, and I don't remember. I don't. Have you told me about this person before? I don't remember, but I have a bad memory, so.
Maybe he can watch. You can watch it on Saturday night with Kip sometimes. So I don't know. I don't know what he's talking about. So anyway, yeah, there's a whole bunch of the. I don't know if I'm saving my
He's
live
probably a
chat.
crackpot.
Probably. Then you'll know everything.
He's a pre-supper.
Yeah.
Okay.
Oh, was that
Yeah.
that was the Joel from last night. It was 3 in the morning. I don't even know. Okay. Okay.
Okay.
Yeah. Yeah, man. Oh my goodness. That was a whole thing. You should go see
I'll bet.
what Nitty put up. It was in the middle of the night. I don't know why I was awake, but anyway, yeah, okay. All right. I didn't know his last name, Kip, so thank you. Appreciate that. So, all right. Well, my brain is full. I don't know. We didn't really talk about the woo, but that's okay because we learned a lot. And what I thought might have been woo is actually not. So that was helpful to me. So I appreciate that.
Yeah. It's that's one of the really sad things about the whole woo thing is that it makes it hard for people to sort of recognize when it is.
Mhm.
Like I mean that paper that those authors put out, that's like the most wooish thing that like I ever see and I frankly I never even see things like that silly in actual like journals. I don't know where they
Yeah.
published it actually. She probably mentioned it.
She put a little thing on there. It was not peer reviewed.
Oh, then it might just be on archive. And
Yeah.
I mean, you
Or
just need to have,
academia or
I think
yeah.
you just need to have like a .edu or actually, I don't know how you get onto archive. I think you might have to be invited by somebody, but that's not a high bar necessarily.
Yeah.
So,
Okay. What about academia ed?
so you might
Is that
you might have to, no, academia.edu is,
Can you just put stuff up there?
Yeah, it's like one of these places like ResearchGate and stuff. Like there's a variety of different things that like I'll try and kind of be like, I don't know, a social network for scientists, and I don't know that any of them particularly are effective. In physics, we just put all our stuff on Archive. Archive
Yeah.
is the preprint archive that most physicists put their stuff on, and you can get most physics papers for free that have been released in the last 30 years just by looking them up and finding them there. And then of course there's Sci-Hub, but I never use Sci-Hub because I can always just get it immediately from Archive. But that's because I'm in physics and we got on that boat early. Some guy at Cornell was like, you know what?
We should do this. Yeah.
It's 1992 and I know how the internet works, so I can make a server and do the thing. And since then, everybody's just been doing that. And journals just kind of like, I think, grit their teeth and look the other way because it's...
Yeah, this was not published in a neuroscience journal, I would agree.
I doubt it was published in a particularly...
Agree with that. Yeah. So... All right. Well, I'm still, I guess I just have a little more studying to do and thinking about some of this stuff because I just don't like superposition the way you describe it. It makes me upset. I'm just like, I'm going to go call Tobias and see what he says. Cause he might make me feel bad.
That's fair. I mean, it didn't make people feel very good that, you know, a brain tumor was very predictive in, you know, how homicidal
people can be. Yep.
Yeah, but I mean, that's how the world works.
Yep. Well, I don't know if you failed.
I have failed peer review before, yes.
Oh yeah, but that
which means actually I passed peer review.
Passed peer review, exactly. Yeah. Everybody knows that. Yeah. So there you go. I mean, there was like 18 different shows in the chat tonight. So I really appreciate you guys very, very much. And anybody new, thanks for coming. If you want to have, join me for in-depth conversations about the Bible, join us some night when we talk about that with Kip or other people that I'm going to have on. So I go over things that I think are interesting. So I hope you guys thought this was interesting too. So
yeah, I had a great time. Thanks for having me.
Cut it out. I'm serious, dude. You need to stop this.
You
didn't make it through the whole. This is the second time. What's going on?
You're a liar.
Yeah. Yeah. Okay. Anyway, you are an atomic physicist, and I will always make sure that everybody knows that.
Yeah.
All righty. Well, I appreciate you being here. Thank you so much for your time, and hope to see you again. Take care.
Yep.
Bye, everybody.